Good evening, everyone, and welcome to York Observatory's TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alan I. Carswell Observatory located at York University in Toronto, Ontario, Canada. TeleTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time. For any questions or comments or suggestions for future topics, please send us an email at observe@yorku.ca. You can also connect with us on Twitter or Instagram with the handle at York Observatory and on Facebook at Alan I. Carswell Obs. I'm Gagan, and I'll be one of your hosts this evening, along with Amin, Austin, Maheen, and Matt. Tonight, we've got a great presentation about the Voyager space missions. Before we get started with our show, we'd like to give you a little update on what you can see stargazing this coming week. Just after sunset around 8 p.m., the constellation Orion will be visible in the southern sky. If you have a telescope or dark skies, try and catch the Orion Nebula, located under the three stars of the Orion Belt. In the west, Taurus and Cassiopeia are visible. The Pleiades, which are an open star cluster visible with the naked eye, are also located in Taurus, and Mars will also be visible during the evening. In the northeast sky, the Big Dipper rises in the evening and will be visible overhead all night. Another awesome object that you might be able to catch with a telescope or a pair of binoculars is the double cluster in Perseus, which can be best viewed early in the night. The moon will be visible for most of the night in the waxing gibbous phase, and the full moon will arrive on March 28th. Try and spot these objects and constellations if you have clear skies and get a chance to stargaze. A pair of binoculars or a small telescope are excellent options to see some of the deeper space objects, such as clusters or nebulae. Let us know what you can see in the chat below. Now, without further ado, let's get started. Austin will kick us off with a little bit about the planning and early stages of the Voyager missions.
Hello, everyone. Thank you for joining us. All great missions have to begin somewhere, and the Voyager missions began with a once-in-a-lifetime alignment. Gary Flandreau, an aerospace engineer, discovered that in the late 1970s, the solar system's outer planets would align. This alignment, which occurs once every 175 years, would make it possible to use the gravity of each of the four giant outer planets to swing a spacecraft from one planet to the next, visiting Jupiter, Saturn, Uranus, and Neptune. With this vision in mind, the Grand Tour project was created. The Grand Tour was a NASA program that would have sent two groups of robotic probes to all the planets of the outer solar system. The enormous cost of the project, around $1 billion, led to its cancellation and replacement with the Mariner Jupiter-Saturn. Mariner Jupiter-Saturn was later renamed the Voyager program because it was thought that the design of the two space probes had progressed sufficiently beyond that of the Mariner family to merit its own separate name. The Voyager project was approved in early 1972, with an estimated cost of less than $360 million for each of the two probes. While the four-planet mission was known to be possible, it was deemed to be too expensive to build a spacecraft that could go the distance, carry the instruments needed, and last long enough to accomplish such a long mission. Thus, the Voyagers were funded to conduct intensive flyby studies of Jupiter and Saturn only. We know how the Voyager spacecrafts came to be, but how were they built? Both Voyager spacecrafts are identical in design. The Voyager spacecrafts each weigh 1,704 pounds. Of this total weight, each spacecraft carries 231 pounds of scientific instruments. The Voyager spacecrafts have 11 instruments, and of these 11 original instruments, only 5 remain functional today. Each of the two spacecraft was equipped with a slow-scan color TV camera to make the images of the planets and their moons, and each also carried an extensive suite of instruments to record magnetic, atmospheric, lunar, and other data about the planetary systems. The computers aboard the Voyager probes each have 69.63 kilobytes of memory in total. For reference, that's about enough to store just one average internet JPEG file. Currently, the radioisotope batteries on Voyager 1 and 2 are diminishing, putting out 4 watts less per year. Mission managers will one day have to prioritize which instruments are most important during the voyage through interstellar space, shutting them off one by one as the years go on. After that, Both probes will remain within range of our antennas until around 2036. More than 10,000 trajectories were studied before choosing the two that would allow close flybys of Jupiter and its large moon, as well as Saturn and its large moon. The chosen flight path for Voyager II also preserved the option to continue on to Uranus and Neptune. The Voyager I probe was launched on September 5, 1977. The Voyager II probe had been launched 2 weeks earlier, on August 20, 1977. Why wasn't Voyager I launched first, you may ask? This was due to the different trajectories of the two crafts. Voyager II needed to travel much further to the two outermost planets, so it was launched first due to the preferable planetary conditions. Despite being launched later, Voyager I reached both Jupiter and Saturn sooner, following a shorter trajectory as Voyager II had been launched into a longer, more circular trajectory. To accomplish their two-planet mission, the spacecraft were built to last 5 years, but as the mission went on, and with the successful achievement of all its objectives, the additional flybys of the two outermost giant planets, Uranus and Neptune, proved possible, and irresistible to mission scientists and engineers. Eventually, between them, Voyager I and II would explore all the outer planets of our solar system, 48 of their moons, and the unique system of rings and magnetic fields those planets possess. The Voyager primary mission was completed in 1989, with a close flyby of Neptune by Voyager II. However, the mission did not end there. Perhaps one of the most interesting aspects of the Voyager spacecraft is that a piece of humanity travels with it. Indeed, NASA planned on an ambitious message aboard Voyager I and II, a kind of time capsule intended to communicate a story of our world to extraterrestrials. The Voyager message is carried by a phonograph record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. The record's cover is aluminum and electroplated. Upon it is an ultra-pure sample of the isotope uranium-238. Uranium-238 has a half-life of 4.468 billion years. The records also have the inscription, "To the makers of music, all worlds, all times," hand etched on its surface. In the upper left-hand corner of the record cover is a drawing of the phonograph record and the stylus carried with it. The information in the upper right-hand portion of the cover is designed to show how pictures are to be constructed from the recorded signals. The drawing in the lower left-hand corner of the cover is a pulsar map that shows the location of the solar system with respect to 14 pulsars, whose precise periods are given. The contents of the record were selected for NASA by a committee chaired by Carl Sagan. The selection of content for the record took almost a year. Sagan and his associates assembled 115 images and a variety of natural sounds, such as those made by surf, wind, thunder, and animals. In addition, they added a 90-minute musical selection from different cultures and eras, spoken greetings in 55 ancient and modern languages, and included other human sounds like footsteps and laughter, and a printed message from then US President Jimmy Carter. Long after the Voyager spacecrafts end communication with us on Earth, they may begin to communicate to intelligent life elsewhere in the universe. Next up, Amin will be discussing in detail the Voyager I spacecraft.
Thank you for the introduction, Austin. Voyager I is a space probe weighing 773 kilograms in total. The spacecraft uses guidance systems and altitude control computers to point its instruments toward the target object and to also point the antennas toward Earth in order to relay the data. As we know already, there are 11 main scientific instruments. Together, they weigh 105 kilograms. The imaging science system uses a two-camera system to take pictures. The radio science system was used to study the physical properties of the planets and moons that Voyager I looked at. There are a few different types of spectrometers which were used for studying atmospheres and radiation. A magnetometer allowed Voyager I to examine the magnetic fields of Jupiter and Saturn. The low-energy charged particle instrument measured energy fluxes and distributions of ions and electrons. The cosmic ray system, as the name suggests, studied the properties of cosmic rays. The Planetary Radio Astronomy Investigation Instrument looked at radio emission signals from Jupiter and Saturn. The Photopolarimeter System gathered data on the surface texture and composition, again of Jupiter and Saturn. Finally, the Plasma Wave Subsystem Instrument studied electron density profiles. Some of the instruments have now been disabled or have become defective. Voyager 1 was launched on September 5, 1977 at 12:56 UTC time. Within a few months, it entered the asteroid belt, and then 9 days later, it overtook Voyager 2. In September of 1978, Voyager 1 exited the asteroid belt. In early 1979, the Jupiter observation phase began. Jupiter and several of its moons were studied. The Saturn observation phase began in August of 1980. Again, both Saturn and some of its moons were observed. The extended mission portion began on November 14 of 1980, and in February of 1990, the solar system family portrait was taken from a distance of 6 billion kilometers from Earth. It is a mosaic of 60 individual frames. One of those images, which is in a later slide, was the pale blue dot image, which showed the Earth as a tiny speck of light. In 1998, Voyager 1 overtook Pioneer 10 and became the most distant spacecraft from the Sun. In 2004, it passed the termination shock area and entered the heliosheath. Within the next few years, several of the scientific instruments were turned off. Voyager 1 entered interstellar space in August of 2012. It is currently still operating in interstellar space and sending signals back to Earth. Voyager 1 made its closest approach to Jupiter on March 5 of 1979. It came within 349,000 kilometers from the center of Jupiter. This close distance allowed for high-quality images, of which many were taken. Observations of the moons, rings, magnetic field, and radiation belt of the Jovian System were undertaken. Our understanding of Jupiter, its moons, and other aspects were greatly advanced by the Voyager missions. Jupiter's rings were discovered, and the first pictures of its atmosphere were taken by the Voyager craft. The Great Red Spot was observed and identified as a giant storm that is moving counterclockwise. 2 new moons were discovered, and on the moon Io, volcanic activity was detected, which came as a surprise because it was the first detection of a volcano on a celestial object other than Earth, and 9 volcanoes in total were recorded. On the moon Europa, a large number of lines were seen. They were initially thought to be cracks on the surface of Europa, but later scientists believed that they were probably similar to ice flows on Earth, which meant that Europa could have water in the interior. A flyby of Saturn was conducted next. The closest approach from Voyager 1 came in November of 1980, when the probe reached a distance of 124,000 kilometers from Saturn's clouds. Complex structures in Saturn's rings were seen, and the remote sensing instruments were used to take a look at the atmospheres of both Saturn and the largest moon, Titan. Many pictures were taken of both the planet and the moons. It was discovered that Saturn is mainly made up of hydrogen, but is 7% helium. Jupiter, by contrast, is 11% helium, so scientists wondered if the difference was because the helium on Saturn's clouds were sinking deeper into the atmosphere. This could explain some of the radiation effects on Saturn. It was found that there are winds on Saturn that blow at extremely high velocities. One measurement found a wind speed of 500 meters per second. Voyager 1 also found auroras and measured the length of a day on Saturn, which is 10 hours and almost 40 minutes. After the family portrait image from outside of the solar system, cameras are deactivated to save energy and allocate resources for other instruments, some of which are still studying the outer solar system today. Voyager 1 is also still traveling at 17 kilometers per second, which is the fastest recession speed from the Sun of any spacecraft. In 1 year, it can travel 523 million kilometers. Scientists believe that Voyager 1 entered the termination shock in early 2003. This is the region where the solar wind, a stream of particles emitted by the Sun, slows down greatly to lower than the speed of sound. This happens due to complex interactions with the interstellar medium. Because the solar wind detector stopped working in 1990, direct measurements were not possible, so the exact time that the probe passed this region is not known to a high degree of precision. In 2005, the consensus was that Voyager 1 entered the heliosheath, one of the outermost parts of the solar system. In 2012, the spacecraft entered the heliopause. At this point, it would take sunlight 17 hours to reach Voyager 1. On September 12 of 2013, NASA officially confirmed that Voyager 1 had reached interstellar space. It is expected to reach the Oort cloud, which is an area with a large amount of comets that surrounds the solar system in 300 years. Voyager 1 is not heading toward any specific star, but in 40,000 years, it should come within 1.6 light years of Gliese 445. Voyager 1 is still sending back information about the heliosphere and interstellar space. Next up, Matt will be discussing the other Voyager craft, Voyager II.
Well, thank you, Amin, for that amazing explanation about the discoveries that we made thanks to Voyager 1. Now, the Voyager 2 was actually launched before the Voyager 1, as it was mentioned before, on August 20th of 1977 to study the outer planets. As part of the Voyager program and its mission, it was launched 16 days before its twin, Voyager 1, on a trajectory that took longer to reach Jupiter and Saturn but enabled further encounters with Uranus and Neptune, making it the only spacecraft to have visited either of these two ice giant planets. Now, on November 5th, 2018, Voyager 2 left the heliosphere and entered the interstellar medium, a region of outer space beyond the influence of the solar system, joining Voyager 1, which had reached the interstellar medium in 2012. Due to a system failure in the primary antenna, it was necessary for engineers to calculate the specific frequency for the signal so that it could be received by Voyager 2 until the end of its mission on October 2, 1989. After having visited the Jovian System in 1979, the Saturnian System in 1981, and the Uranian System in 1986, as well as Neptune. Voyager 2 began transmitting images of Jupiter in April 24th of 1977 for time-lapse movies of atmospheric circulation. Unlike Voyager 1, Voyager 2 made close passes to the Jovian moons on its way into the system, with scientists especially interested in more information from Europa and Io. Voyager's 2 closest approach to Jupiter occurred on July 9, 1979, when it came within 570,000 kilometers of the planet's cloud tops. Voyager 2 returned images of Jupiter as well as its moons Amalthea, Io, Callisto, Ganymede, and Europa. During a 10-hour volcano watch, it confirmed Voyager 1's observations of active volcanism on the moon Io, and revealed how the moon's surface had changed in the 4 months since the previous visit. Together, the Voyagers observed the eruption of 9 volcanoes on Io, and there is evidence that other eruptions occurred between the two Voyager flybys. Jupiter's moon Europa displayed a large number of intersecting linear features in the low-resolution photos from Voyager 1. And 2 new small satellites, Adrastea and Metis, were found orbiting just outside a ring. A third new satellite, Thebe, was discovered between the orbits of Amalthea and Io. Following a course correction, 2 hours after its closest approach to Jupiter, Voyager 2 sped to Saturn. Its trajectory was determined to a large degree by a decision made in January 1981 to try to send the spacecraft to Uranus and Neptune later in the decade. Its encounter with the 6th planet began on August 22, 1981, 2 years after leaving the Jovian System. With imaging of the moon Yapyrus, once again, Voyager 2 repeated the photographic mission of its predecessor, although it actually flew about 23,000 kilometers closer to Saturn. The closest encounter to Saturn was on August 26, 1981, at a range of about 101,000 kilometers. The spacecraft provided more detailed images of the ring and also the F-ring and its shepherding moons, all found by Voyager 1. During the encounter, Voyager 2 also photographed the Saturn moons Hyperion, Enceladus, Thetis, and Phoebe, as well as the more recently discovered Helene, Telesto, and Calypso. And although Voyager 2 had fulfilled its primary mission goals with the 2 planetary encounters, mission planners directed the veteran spacecraft to Uranus, a journey that would take about 4.5 years more than what was planned. After such a long trip, Voyager 2 became the first human made object to fly past the planet Uranus. Long range observations of the planet began on November 4, 1912, when signals took approximately 2.5 hours to reach Earth. The closest approach to Uranus took place on January 24, 1986, at a range of about 81,500 kilometers. During its flyby, Voyager 2 discovered 10 new moons, two new rings in addition to the older 9 rings, and a magnetic field tilted at 55 degrees of axis and off center. Voyager 2 also returned spectacular photos of Uranus' larger moons, including Miranda. Flying by Miranda at a range of only 28,000 kilometers, the spacecraft came closest to any object so far in its nearly decade long travels. Following their Uranus encounter, the spacecraft performed a single mid-course correction on February 14th of 1986, which was the largest ever made by Voyager 2, in order to set it on a precise course to Neptune. Voyager 2 was directed into a path of about 4,950 kilometers above the north pole of Neptune. 5 hours after after Voyager 2 made its closest approach to Neptune, it performed a close flyby of Triton, the larger of Neptune's two originally known moons, passing within about 40,000 kilometers, revealing the coldest known planetary body in the solar system and a nitrogen ice volcano on its surface. Voyager 2 also discovered 4 previously unknown Neptunian rings and confirmed 6 new moons: Despina, Galatea, Larissa, and Proteus, Naiad, and Thalassa. Images reveal details of the 3 major features in the planetary clouds: the lesser dark spot, the great dark spot, and the scooter. The Great Dark Spot has actually since disappeared, and it's now theorized to have been a window of clear clouds, allowing us to see the methane cloud deck. The flyby of Neptune concluded Voyager's 2 planetary encounters, which spanned an amazing 12 years in deep space, virtually accomplishing the originally planned grand tour of the solar system. Later on, Voyager 2 started its current mission, which is the same mission as it was mentioned for its twin probe, to travel through the interstellar medium. Maheen will tell you about this part of the mission now.
Thank you, Matt, for enlightening us with what Voyager 2 is all about. Moving on. The Voyager mission is the longest running and most distant mission in history. Although Voyager spacecrafts were only designed to last for 5 years, they have broken all previous records and outlasted their operational lifetime, such as that of Pioneer 6. They were initially launched only to fly near Jupiter and Saturn. The spacecrafts are now in interstellar space. Voyager became the first ever human-made object to cross the thresholds of interstellar space, which opens doors for more discoveries. Voyagers are traveling at 35,000 miles per hour and will not run out of fuel until 2025. Does this mean the year 2025 is the end of Voyagers? Well, not exactly. Even after running out of power and fuel, they're expected to continue their journey. As said by Bill Kurz, researcher at University of Iowa, quote, "They are in their own orbits around the galaxy for 5 billion years or longer, and the probability of them running into anything is almost zero." Unquote. Eventually, the Voyagers will approach other stars. In approximately 40,000 years, Voyager 1 is expected to be within 1.6 light years of the star AC plus 793888, and in 40,000 years, Voyager 2 will be 1.7 light years from the star Ross 248. NASA's interstellar mission played an important role in all of this. NASA's Voyager Interstellar mission began when the Voyager primary mission ended in 1989 with Voyager 2 flyby of Neptune. When this mission began, Voyager 1 and Voyager 2 were at a distance of 40 astronomical units and 31 astronomical units from the Sun, respectively. For reference, the distance between Sun and Earth is 1 astronomical unit. The mission began in an environment where solar winds were under the influence of Sun's magnetic fields and had supersonic speeds. There were three major phases of this mission: the termination shock, the heliosheath, and the interstellar medium. The termination shock is where the speed of the solar wind reduces to subsonic speed and compress, resulting in heating. Changes in the direction of the magnetic field also occur. After this, the phase of heliosheath exploration started. Heliosheath is the outer layer of the cavity Sun forms around itself called the heliosphere. This phase was still dominated by solar winds and Sun's influence, including the magnetic fields and particles of its solar winds. The third phase began where the Sun's influence started to wane and the interstellar medium phase started, discoveries of which continue till date. The Voyager spacecrafts made some important discoveries about the interstellar space which were contradictory to some of the assumptions made by scientists earlier. Unexpected differences in density of plasma was observed by the scientific instruments of Voyager II. Plasma is a collection of charged particles existing in the solar system. Density of plasma across the heliopause, which is the border of the solar system, increased by a factor of 20 to 50. The data acquired from the Voyager 2 also suggested a much simpler and thinner heliopause than suggested by Voyager 1. It was also observed that on approaching the interstellar space, the solar wind slowed down to zero outward velocity in the stagnation region, although it was expected to turn to the corner due to interstellar magnetic fields and winds. Voyager 2 also confirmed the existence of a magnetic barrier at the outer edge of the heliosphere, which was predicted before, although it was discovered that the magnetic barrier was not smooth, rather in the form of magnetic bubbles which are millions of miles wide. This magnetic barrier keeps the dust, debris, and radiation out of the solar system, just like Earth's magnetic field protects it from solar radiation and cosmic rays. The data received from Voyager 2 showed a smooth change in direction of magnetic fields from when it arrived at the magnetic barrier, traveled through it and through the interstellar medium with a very minor to no change in the heliopause, which combined with all the findings suggested that the magnetic barrier, heliopause, and local interstellar space form a complex interconnected dynamical system. As mentioned previously, Voyager mission was launched in 1977. It's been 43 years and 7 months since then. The current distances of Voyager 1 and 2 just 30 minutes before our TeleTube broadcast was 152.320 AU and 126.581 AU from the Sun respectively, and they are not stopping anytime soon. They have enough thruster fuel and electrical power to keep them going until 2025, by which Voyager 1 will be 13.8 billion miles from the Sun, and Voyager 2 will be 11.4 billion miles away. Voyager 1 is currently in the constellation of Fucus. NASA had lost contact with Voyager 2 for 7 months in 2020, for which it was flying on its own due to repairs required by the radio antenna DSS-43 in Australia that is used to control it. Luckily, after repairs and some improvements, the contact with Voyager 2 was re-established on 29 October 2020. Scientists are eager to find out how interstellar radiation will impact future space exploration. At the start of the mission, the distance to the solar bubble was not known, and there were no expectations for Voyagers to make that far. But this opened the door for deep space research. As said by the chief scientists of Voyager mission, Ed Stone, quote, "It's the first journey between the stars. It's like sailing on the ocean for the first time after leaving land. We're out in the cosmic sea. Most of the universe, by the way, is this kind of interstellar stuff. This will give us information about most of the volume of the Milky Way." Unquote. It will be the first time in history scientists will get to study interstellar winds, movements of the heliosphere, and also galactic cosmic rays. Since Voyager spacecrafts have now crossed the heliosphere, all the theories can be backed up by proper evidence, and there can be immense growth in astrophysical research. In regards to the final frontier of the Voyagers, no one really knows, but it can be predicted to last till where Sun's gravitational grip extends to. A new insight and a new way of looking at research came to minds with this amazing ongoing journey of the Voyager. It really raises the question as to how far can we go and where can this mission lead us. Well, everyone, you have been listening to the Ellen I. Carswell Observatory's weekly TeleTube broadcast, the Astronomy and Astrophysics program, written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Amin, Austin, Matt, Gagan, and myself, Maheen. Make sure to leave any comments or questions in the comment section of the video below and talk to us in the chat right now. We will be around for the next 20 minutes to answer your questions. All of our programs are free, but if you would like to make a donation or buy one of our astrophotography calendars, see our website at observatory.info.yourq.ca. You can always connect with us on Instagram and Twitter with the handle at York Observatory, as well as on Facebook with the handle at Ellen I. Carswell Ops. And check out our website for show notes, content, updates, and contact info at observatory.info.yourq.ca. Thanks for tuning in. Clear skies and have a good night.